Welcome to the lecture series of Abstract Algebra, part 1 of Module 1. For reference, we can use the book A First Course in Abstract Algebra by John B. Fraley. In this part, we are going to discuss about binary operations and few examples. Binary operation. To define a binary operation, we need a non-empty set. Here it is denoted as S and an operation star. The set is said to be non-empty, which contains at least one element. And the operation star may be the ordinary or usual operations like addition, subtraction, division, multiplication, etc. So the definition of binary operation is like this. Let S be a non-empty set. A binary operation or a binary composition star on a set S is a mapping which associate to each ordered pair AB of elements in S. A uniquely defined element C denoted by A star B of S. That is, star of AB is equal to A star B. Here C denotes the product A star B and the element A star B must be an element in S. Then we can say that star is a binary operation on S. Instead of star, we can use the notations like star dash, plus, multiplication, etc. And also, star must be well defined on S. Means exactly one element is assigned to each possible ordered pair of elements of S. That is, if we consider any two elements A, B belongs to S, then star of AB must be some C. And we cannot get another element some C dash. If we get some element C dash, then C must be equal to C dash. That is, the resulting element must be unique. And another condition is S is closed under the operation star, which means for each ordered pair of elements of S, the element assigned to it is again in S. That is, the resulting element must be an element in S. Actually, the star is a mapping from S crosses to S. Now we can go through some examples. First we consider Z plus, that is the set of all positive integers, or it is also known as natural numbers. The addition and multiplications are binary composition in the set of all positive integers. Since if we take sum or product of any two positive integer, then the resulting element must be a positive integer. That is, for example, if we consider the elements like 3 or 3 and 5, then plus of 3 5 is equal to 3 plus 5, that's equal to 8, must be 8 belongs to Z plus. Also, product of 10 comma 2 is equal to 10 into 2 is equal to 20. It's again a positive integer. So this is true for any positive integer. That is, in general, if we consider any two elements A comma B belongs to Z plus, then plus of AB is equal to A plus B is again a positive integer. Also, product of A comma B is equal to A into B is a positive integer. But in the set of all positive integers, subtraction or division are not binary operations. The reason is, if we consider the elements like 4 comma 9, minus of 4 comma 9 is equal to 4 minus 9. That is a negative number minus 5, which does not belong to Z plus. Also, if we consider the elements like 5, 15, etc., that is the elements like A comma B, A less than B, then division of 5 comma 15 is equal to 5 by 15, that's equal to 1 by 3, is a fraction which does not belongs to Z plus. Also, instead of this ordinary operations like addition, subtraction, division, multiplication, we also define other operations like star. One operation is explained here. Here we define star by A star B is equal to the smaller of A and B, or the common value if A is equal to B. Then star is a binary operation. Now you think about how many binary operations are possible in Z plus. Try to find out at least two other than we already explained here. Second example is Q, the set of all rational numbers, which is closed under addition, multiplication and subtraction, and these operations are well defined on Q. That is, if we consider any two element a, b in Q, a plus b again in Q, a into b again in Q, a minus b are again in Q. But what about the division? Division is not a binary operation in Q. What is the reason? 0 is also an element in Q, and division by 0 is not defined in Q. Also think about, is it possible to define division as a binary operation in Q by putting some restriction on Q? That is, if we restricting some element or avoiding some element from Q, is it possible to define division as a binary operation Q? And what about R, the set of all real numbers, set of all positive real number and numbers under various operations? Third example is, if for any non-empty set S, consider P of S, means the power set of S. Power set of S means set of all subsets of S. Then we know the usual operation in power sets like union and intersection. These two operations are binary operations in power set of a set, because union of any two subset is again a subset and intersection of any two subsets is again a subset. The fourth example is, let V be the set of all vectors in space. Then the operations of vector addition, vector subtraction and vector multiplications are binary operation as for. What is the reason? If we take any two vectors, adding two vectors we get another vector, subtracting one vector to another vector we get a third vector, and multiplying two vectors we get another vector. So these operations are binary operations in set of all vectors in a space. Think about, if we consider the set of all coplanar vectors, that is the vector lying in the same plane, then can you guess which among these above operations are not binary? What is the reason? Already we discussed about the operations in set of all vectors in a plane, that are addition, multiplication and subtraction. So the question is whether these operations are binary in the set of all coplanar vectors. And next one is dot product is a binary operation in the set of all vectors in space? Actually, if we take any two elements from the set, the resulting vector after our starring operation, the resulting element must be the element of S. So here is the question is like this: is dot product a binary operation in the set of all vectors in space? So we want to check whether the resulting element must be a vector. Fifth example, if M denote the set of all M by N real matrices with real entries, here M denote the number of rows and N denote the number of columns, then the operations of addition, subtraction of matrices are binary operations. Next one is, let F be the set of all real valued functions having as the domain the set R of real numbers. Then the operations addition, subtraction, multiplication, composition are binary operations in F. That is, if we consider set of all real valued functions, then adding to real valued function, the resulting function must be real valued. Subtracting one real valued function to another real valued function, the resulting function must be real valued. And the same is happening in the case if we take in the product of two functions. And the another operation is composition. Composition of two function is another function. So if the two functions are real valued, then the composition of that two functions must be real valued. Seventh example is a special example. So here we are going to define a new operation, addition modulo n. The operation is like this: a plus modulo n b means adding two numbers a and b, and after dividing this sum by n and we only consider the remainder. That is, if a and b are any two integers, addition modulo n of a and b is defined by a plus modulo nb is the least non-negative integer obtained as remainder when their ordinary sum a plus b is divided by n. That is, for example, for any n belongs to z plus, let zn is equal to set 0, 1, 2, etc. n minus 1. That is n elements contained in this set. Then the operation plus modulo n is a binary operation on zn. For example, if we consider z3, then z3 n is equal to 3. There are 3 elements and the set include the elements 0, 1, 2. Then the addition modulo 3 is defined here like 1 plus 2, 1 more plus modulo 3, 2 is equal to add in 1 and 2, then we get 3, dividing 3 by 3, the remainder is 0. So the resulting element must be 0. 0 belongs to Zn. So the set of all Zn under addition modulo n is a, here addition modulo n is a binary operation. Think about in example set. Is there any way to make m in such a way that metric multiplication is a binary operation? That is, m here in the fifth example, we consider m be the set of all m by n matrices. That is, there are m rows and n columns. So by changing the pattern of that set of all matrices, is it possible to define multiplication is a binary operation in M? Next one, if possible, define a binary operation in the set of all matrices with real entries. Here is some problems. First problem, let S be the set having exactly one element. How many different binary operations can be defined on S? Answer the question. If S has exactly 2 elements, exactly 3 elements, exactly n elements. So here we want to count the number of binary operation on a set S with different cardinality. Cardinality means different number of, cardinality means the number of elements in that set S. Second question, let addition and multiplication be the usual binary operations of addition on a set Z, and let H is equal to set of all n square such that n belongs to Z plus. Determine whether H is closed under addition and multiplication. That is the second question. Here Z is a set of all integers with the usual operation addition and multiplication, and H is a subset of Z. H contains the elements like n square when n is a positive integer. So H plus and H multiplication, check whether addition is a binary operation or H, or multiplication is a binary operation on H. Third question, draw the composition table of the binary operation plus modulo 6 on the set Z6 is equal to 0, 1, 2, 3, 4, 5. This is the solution of the first problem. So here, as we know, star is a mapping from S cross S to S. Here, if S has only one element, then what happened? Number of element S cross S has only one element. Hence the number of functions from S cross S to S is 1. Therefore, number of binary operations on S is 1. The second case, if S is a set having only 2 elements, then S cross S has 2 into 2, 4 elements. Therefore, the number of function defined from S cross S to S is order of S raised to order of S cross S. That is 2 raised to 4 is equal to 16. Therefore, the number of binary operations on S is 16. Likewise, if S is a set having 3 elements, then the number of functions from S cross S to S is order of S raised to order of S cross S. That is equal to 3 raised to 9 is equal to 19,683. Therefore, the number of binary operations on S is 19 683. Okay. Now the case where the number of element in S is n, then S cross S has n square elements, and therefore the number of functions from S cross S to S is n raised to n square. Therefore number of binary operations of S is n raised to n square. Therefore we can say in general, for any set with n elements, then the number of binary operations defined on S is n raised to n square. The answer of the second question. So second problem is like this: Z is the set of all integer and H is a subset of Z. H is equal to set of all n square such that n belongs to Z plus. Okay, first we want to show that plus addition is a binary operation on H, that is whether H is closed under addition. Since 1 square is equal to 1, 2 square is equal to 4, therefore 1 comma 4 belongs to H. But 1 plus 4 is equal to 5. 5 does not belong to H because 5 is not a square of any positive integer. Therefore H is not closed under the operation addition. Okay. And the second case, if we choose any two elements like R comma S belongs to H, then R and S is power of some positive integers, that is R is equal to n square and S is equal to m square. Then Rs is equal to n square into m square, that is nm square. Since Z plus is closed under multiplication, nm belongs to Z plus. And also Rs is equal to nm square belongs to H. Hence H is closed under multiplication. Means multiplication is a binary operation on the set H. And the solution of the third problem. Third problem, we want to draw the multiplication, the table of addition modulo 6 of the set Z6. So if we consider any two element a comma b belongs to Z6, a plus modulo 6b is equal to the least non-negative integer obtained as remainder when their ordinary sum a plus b is divided by 6. That is, if we consider any two elements of the set, and for example if we consider 5 plus 2, 5 plus modulo 6 means adding 5 and 2 we get 7, dividing this 7 by 6 we get the remainder 1. Therefore 5 plus modulo 6 2 is equal to 1. Also 0 plus modulo 1 is equal to 1, 0 plus modulo 2 is equal to 2, etc. 5 plus modulo 5 plus modulo 6, 5 is equal to 4. Now consider the table is here. This is the table of our problem. So here we have the rows and 6 rows and columns, and the resulting elements is included in the interior of the table. Thank you for watching this video, and the second part is coming soon. So in this first part we discussed only about the binary operation and some examples of binary operations. Thank you.